Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my pleasure to welcome Bruce Gooch here today. Bruce and I both got our PhDs from the same institution, University of Utah. I got mine a little bit earlier. Since then, he's been professoring around the country at Northwestern, north of Chicago, and for the last number of years, just north of here in Victoria. In addition to professoring, he's been taking a lot of the work that's come out of his research and turned it into product, which I hope he'll talk to us about today as well, through various startups, I guess.
Mm-hmm.
Anyway, Bruce,
thank you, Michael. So, like Michael said, I'm Bruce Gooch. Just call me Bruce. If you have any questions, stop me, ask them. Comic Tycoon is a product, an app that my company, Insatiable Genius, just dropped. And if at any time I get it boring, all the technology that I'm going to talk about is available for free in the Windows Store. So you can get these apps for free, try them for 2 days, see if you like it. But it's Comic Effects on the Windows Store. Like I said, I'm Bruce Gooch. I pretty much I started out doing non-photorealistic rendering. Cameras anymore are ubiquitous. Most of us probably have one on us. The crazy thing is, about 80% of the images that humans create are non-photorealistic. We create art, it's what we do. Right now, my focus is creating tools that allow people to create content, to create digital content. And the best content, the ones that I like the most, are the ones that can cross over. I can do stuff in the real world and it has some some digital component, or I do something in the digital world that gives me some real world artifact. Okay, so as Michael said, in addition to being a professor, for the last 3 years, I've been running a startup incubator in my lab. So if you look at my Vita, I'm a little light on publications for the last couple of years. On the plus side, we've started 19 companies. I have 4 multi-million-dollar stable companies that have come out of the lab. Insatiable Genius, TuneFX, Gaslamp Games, DJ Arts Games. I've been working with the CogMed guys. We did a startup with them and we're building applications, medical applications, for kids who have panic attacks. Anyway, there's lots of stuff. Relevant Games has been building games with embedded cognitive therapies for kids with ADHD. Like I said, it's worked fairly well. Part of the reason is Victoria, and it's part of the reason that I left Northwestern to go to Canada. We own everything we build. The university just signed off on it. They have I got a blank check for inventor-owned IP, which just didn't exist in the US at any of the universities that I went to. And so I was able to do this. The other thing is BC, for some reason, is 60% of the people in British Columbia run their own business. It's the largest concentration of self-employed people on the planet is Vancouver. Who knew?
Why 19 instead of 1? Or 2?
Oh, they're not me. Sorry, I'm just a facilitator.
So
I did Insatiable Genius and TuneFX.
Okay.
Everything else is my students.
So each student will go off and just try to commercialize what they do.
Yeah, yeah, and they've kind of watched me, and part of this is an exploratory process. They've watched me make a whole lot of mistakes, and they've watched my few successes, and they're like, Gooch is making money, I can do this, and then I just tell them what to do, and I give them space in the lab. Like the jetpack laser cat, it was 3 students that took my freshman game design class, and they came to me, they had this really cool final project. I said, hey, you should do this on an iPad, and then I just gave them space in the lab over the summer. And I gave them computers and I let them work in the lab. And they showed up every day. I showed them how to incorporate in Canada, how to get a bank account, and how to start stuff on the iPhone. And they did it.
And is the fact that the university gives you the IP or allows you to keep the IP, is that a conscious decision on their part, or are they just, the exception to the rule and they just happen to be that way?
Or are they just clueless?
Yeah, like are they going to wake up someday and say, wait, we should be like everybody else and hold on to the IP? Or are they trying to foster?
They just need 1 or 2 huge successes.
I think that if they get an HP or a Google, that switch will flip. But so far, they get a lot of mileage out of it. Because there's an incubator in Canada called Enterprise, and my numbers are better than Enterprise. So like I said, they're getting mileage in the alumni magazines and all kinds of stuff. And then one of the deals that I cut with my students, I show them how to do operating agreements, and I'm like, do this and you'll never get in trouble. If you do 2% of your profit, of your net, and say that I'm going to start a scholarship program for computer science students at UVic with that 2% of my net, nobody's ever coming after you. And so they've all done that, and the catch for them is, well, they got to make money.
It's like a mafia agreement.
Right. Being a faculty member, right? But, 2% is 2%, and you've got to make money, and so they're all over it. And everybody's like, oh, that's fair, I'll do that. That sounds great. Okay, so I've released a bunch of apps, and this is through Insatiable Genius. Tune Paint is one, and this is research that I started forever ago. Take a picture, make something that looks like a cartoon, just a black and white, and then you can paint it in with your finger, paint in colors. That one has about 3 million users now, and it's on iPhone, Android, Windows 8, and then Samsung. Pencil Effects, we dropped this one last fall, about not quite a year ago. And this is a new engine that we developed over the summer. Take a picture and it'll give you something that looks exactly like a pencil drawing. And this one has about 50,000 users. Okay, so that's what I've done. And I'm going to pull back the curtains here, and I'm going to show you how I do it. And I kind of look at art. I have a 3-part process for working. I look at art and psychology and computers, and I get ideas kind of from all 3 of them. We did a color to gray algorithm, and it came from looking at a book by Margaret Mitchell, the psychologist. A lot of the work that I do has been non-photorealistic. I'm making art, and it's really tough to sell art to a computer science crowd, right? Why should I care? You're making art. And so what I started doing is looking at psychological evaluation. I'm going to make an image that's going to make it easier for you to perform a task than a photograph will, right? We all know that, like a technical manual. Certain images that we make are better at, say, facial recognition. And if I can measure a performance increase, then that's something that is a validation of this type of work, right? And then sometimes it's computers. I find a new tool, that tool makes something that looks like art, or that tool enables me to tweak some psychological process, right? Some cameras make really good edge images. Some let me see into the infrared, and there's things I can do with infrared. Some give me depth. Well, if I've got depth, what can I do? So usually there's some inspiration, but I'm trying to combine these 3 things. Another one is known versus unknown, right? Usually I'm pretty happy if I don't know what's going on, because if I don't know what's going on, then maybe no one knows what's going on, but then you have to check yourself, because I'll run into things, I don't know what's going on, but do I have to go back to the book or somebody else's book? So there's this interplay, right? Is this thing known or is it unknown? Do I need to go read the papers? Is it in the papers? Is it in the book, right? And then this idea of top-down versus bottom-up. A lot of what I do is very bottom-up, right? I play with things. I look at them. I put together image filters until it looks like art. But then you've got to back off and say, what's going on here? Why does this work? Why does this produce this result? Or why does this, can I look at the bigger picture? Is there a bigger picture? Does this mean anything to computer science at all? So it's, once again, this thing where we do the close-up, we do the high view. And like I said, usually I'm close and I try and work on things I don't understand versus things that I do. So today I want to talk about comics and this comic process. This is a crazy thing. Ever since humans have had writing and art, we've made comics, right? It's one of the first things that people do when they invent new languages. Let's start making comics. I'm gonna do a picture and a thing. So the Bayeux Tapestry, the Ronin, the Egyptian hieroglyphics. They're also amazingly effective, right? The 9/11 comic actually outsold the 9/11 report. More people read the comic book than read the report. As far as imparting technical information, they're fantastic. Process information, do this, do this, do this. The US military still uses a comic that was developed in World War II called, the soldiers call it How to Love Your Rifle. But it shows you the cleaning and the operation of a military weapon. And it's a comic book that you get. They also give you one that shows you how to file your taxes. Turns out it's 80% more effective. 80% more soldiers file taxes if you give them the comic book than if you give them a sheet that shows them how to do it. Right? Images and words. We put them together, you get more than one or the other. So why don't we all make comics? And the big one is the crisis of realism, right? I want to paint that. You know, I want to paint this, and boy, oh boy, I paint that. Right? The other one is schools don't really value drawing in North America. By 5th or 6th grade, I'll get half an hour of art as an enrichment activity once a week. And usually they just let you go. Okay, guys, here's a piece of paper, draw something. You know, so I draw a stick figure, the guy next to me draws something amazing, and I quit. Crumple, crumple, crumple. Well, we're done with that. Right? And that's what I can do. Right? I can take, what I knew was, I could take a picture and I could give you something that looked like a comic. And what I really thought in the beginning was, I'll just put bubbles into Toon Paint. And it didn't work. It makes this. And so I went back to the drawing board. And I came up with a 5-part process. This is how people go about creating comics. I just, once again, unknown, I don't know how to do it. I go to the known, I got every single book I could find, and I read through them until I came up with a process. And then I have a lot of Facebook friends that are comic artists now, and I just asked them questions. How do you do this? How do you do this? How does the process work? Well, there's a penciler, and there's an inker, and there's this guy, and there's that guy. The big one, the first big thing is composition. We all take photos. There's tools on my phone that show me how to take a photo, where to line stuff up. The problem with a comic is I've got to leave enough room in my composition for the bubble. Right? And then I've got to have some kind of eye control. Because if you look at most comics, there's something about the way my eyes work and the way that it makes my visual process work. Right? My macula will track in a certain way. So like this guy's eyes kind of point, or his nose line points toward that bubble and draws your attention to it. When we start putting together panels, it becomes even more complex. And this for me was pretty cool. I've done a lot of work in composition. I built tools that helped you simulate the work of Jackson Pollock. And one of the crazy things about Pollock paintings is everything hits the same fractional dimension. He hits a very small range in the fractal dimension with his paintings. And you can show that he went in and cropped to hit this fractal dimensionality. There's a physicist named Richard Taylor at the University of Oregon who studied this forever. And so I just built a coaching tool that helped you. Okay, if you put some more fine stuff here, you'll get closer and closer, and you want this fractional dimensionality to be about 1.7. And it turns out to be freakishly difficult to get things near 1.7, but then when we did forced choice experiments later, things that were closer to 1.7 were actually, the audience liked them more. If I give you two things, one with the 1.6 and one with the 1.7, you like the 1.7 on average. People on average like the 1.7. They did more than they like the 1.6 or the 1.8. So it seems to work. This is one that I did. This is, once again, looking at a mobile device. Let's say you're out whale watching, you see the whale, your wife takes a picture of you, and you want to send it to your grandma on a mobile phone. We kind of have a couple of options, right? I can crop, I can scale, which in my case is wonderful, because I just lost like 40 pounds. Or we can chop the image apart, put it back together in a way that gets the important things all into an image that fits into a small speck, right? And I'll talk a little bit more about this later. But that worked pretty well, and what we're doing is combining computer graphics with some machine vision, a little bit of artificial intelligence to recut these images to fit a given size specification. Once that worked, we did the same thing with vector animations. And this worked really, really well, because in SVG, I just have a tree that's this image. I can annotate things or give them a weight, and then as the things get smaller or larger, we change based on these weightings. And this worked really, really well for informational images, right? Because in Canada, well, I need to see what these numbers are, right? And if I do a uniform, right, if I lose information in my image uniformly, I'm going to lose important information. If we can annotate importance, then we can resize in a better fashion. For the Wally Wood stuff, for the comics, I tried everything, and what I fell back on was I found this thing that Wally Wood made called Panels That Always Work. And Wally is the guy who wrote the original comic with Stan Lee when they were in the military in World War II that showed soldiers how to file their income tax forms. And Wally had made this poster and he put it on the wall behind his desk that said, hey, don't reinvent the wheel with every panel you draw. Just use these most of the time. And so I basically what I built was just that. It's a Wally Wood composition tool. You choose a panel, and I can show you either of them or let you cycle through them. Choose a panel, and I just put it on your camera, right? So you aim your camera, move the camera, put you in there, snap the shot. Like I said, this is one where there wasn't a whole lot of technical you know what I mean? I didn't reinvent the wheel. I went out and found something that worked and I used it instead of doing something with a whole lot of technical difficulty. The next thing was a new incline algorithm. And one of the problems on a mobile device is that there's just a limit to the computational complexity that I've got, right? When we started doing this on an iPhone 3, I get the computational complexity of a stopwatch. The modern stuff, I get a GPU, but I'll suck your battery dead in no time. But what I really need is something that works fairly well and is consistent. If it takes 10 seconds, it takes 10 seconds. And then on the devices, when we went to Windows 8, I get a whole lot more pixels and a better computational model, and I get more memory. So it actually worked really well. And this is based on some work. I actually started this for my dissertation about 12 years ago. This work we published at SIGGRAPH in 2006 with 2 of my graduate students. And basically all we're looking at is difference of Gaussians. And with Cameron here, what I'm trying to do is draw these edge lines, just wherever you see the black lines. So that would be the basics of the comic. And all this is difference of Gaussians. I'm going to use a Gaussian filter, run multiple Gaussian filters, and difference them to make an image stack, right? So multiple blurs of the image, do a difference between these things, and it finds these edge lines. The problem is, if you look at Cameron, it looks a little better on my screen, but those lines are really harsh, right? It doesn't look like a comic. It looks very pixelated. Okay, so we smooth them. This was kind of the other contribution there. We used anisotropic diffusion to smooth everything. And what we found is we could run multiple iterations of the anisotropic diffusion and then the Gaussian differencing. And then one other thing is when you look at an edge, we usually think of an edge. So this is what the raw output of the Gaussian stack looks like. And we're going to do a thresholding step to decide where an edge is. And usually what we get is some sort of impulse, right? A step function. This is an edge. This isn't an edge. And we just started looking at them as a tanh function. And this gives us this kind of softened edge. And that's what we were doing about 7 years ago. And 7 years ago, on a good computer, on a fast computer, I could get this to run at about 20 frames a second, right? And it produced at 640 by 480, and it produced a kind of jaggy video, but it worked. Like I said, it worked. The stuff that I do today is crazy because the other thing that you do when I do, okay, so I'm going to go out and I'm going to make better edge lines. I'm going to make better video. And my goal here was to be able to make something that looked like a comic, have a still image that looked amazing, looked like a comic book image, but have something that would run fast enough that I could do video. Now, today, video on a mobile device, you can do it, but there isn't a whole lot of video sharing. There's kind of 2 companies that are doing it right now that are trying to do the kind of Instagram thing with video. You're limited to 6 seconds, 640 by 480 in most cases, and it just hasn't caught on. People aren't doing it. But I'm saying, okay, I'm going to position my company for the future. We're going to try this. So the first thing I did is I started building tools, because I knew that I wanted to be able to do this low-level thing. I want to be able to program in Matlab, right? And look at these filters and these iterative filters, and things are going to be going crazy. You know, my diagram before was fairly straightforward. I'm going to do an edge image, and I'm going to do a color image, and I'm going to do a compositing step and get a final thing out. If you ask, I'll send you my other one. It's a giant spaghetti of things. We're basically mimicking a lot of visual processes that happen in the human visual system. So I've got feed forward and feedback, and I'm using the edge lines to inform the color process and the diffusion process and all kinds of things that are going on. And it's kind of the secret sauce behind everything. But what I knew that I wanted to do is be able to prototype in Matlab, because I figure if I'm not working in Matlab, I'm not doing anything that's cutting edge. I'm just refining somebody else's solution. But I want to see this thing work on a GPU on a mobile device. So Brad Larson is a chemistry student, and he'd built a system that would allow you to work in Matlab using image processing tools, and it would automatically kick out GPU code. So we started leveraging his stuff, and we actually worked with him quite a bit. We debugged a lot of his stuff. And then we ported it to Android, and that's out there. You can download it on GitHub right now. And then we ported it to Windows 8, and I haven't released that code because I know that it only works on a single Nokia phone. So the Nokia guys were happy with it. It was selling apps, and we're like, okay, that's as far. We're not letting the other developers touch it at this point. So that's the first step. I'm going to build some tools so I get to play with everything. And this ended up paying off really big time later on, because the memory requirements for what we're doing are vast. So what I do in our apps, when you're changing things, like if you go into the app and change buttons, like you're using a large, medium, or small filter, we're actually generating a shader on the fly. It ends up being about 17,000 lines of shader code that we generate. And after that, we just use your shader, right? And the higher order parameters that you get to move the sliders, you get to play with, and those are feeding into your shader. We're actually building a shader on the fly for you. So this worked out really well for us. Okay, so these should play. This should be a video. And bad things seem like they're happening. Come on, baby, play. Oh no. Okay. Doesn't matter. This is, Thor versus the ice giant in my backyard with me and the neighborhood kids. And basically what happened, if this video was playing, you'd see that it's pretty noisy. And this is my first pass on this kind of stuff. And I'm getting noise in two ways. I'm getting noise from these edge lines, and then I'm getting quite a bit of color noise back here. So I went through and tuned everything that I could. Yeah, I'm just using diffusion and the soft quantization. Once again, if this were playing, this is after that Valkyrie has stabbed me, and I'm laying here on the ground. I'm getting a lot of noise over here in the background where the trees are. And the trees are moving, but they're in shadow. So I looked at parameter variations, but it turned out that if you do a bit of analysis, most of my noise is coming where edges are. Right, I'm getting the bulk of the noise in edges. I look at everything. I looked at all kinds of parameters. And once again, I can mail you these slides. You'll just see that it's crazy noisy. And I wasn't really able to get rid of a lot of the noise from these things. And what it turns out is that the problems are low light and texture. And you can see on this, these are a couple of images. I believe it's Scarlett Johansson. Low light areas were what were the worst for us. And then these high texture areas. Right. And here's another example. This is a finer grain. But you can see that everywhere where I've got like her hair right here, this is the worst because I've got low light and the repetitive texture.
These are all videos?
These are images.
Yeah, okay.
Video stopped here.
Okay.
So what I did, and the whole thing behind what I've been doing since 2006 is it's very low level. If I get rid of all the noise in a single image, right, if I decrease the noise as far as we can in a single image, it seems that seems good enough when we move it to video. And I was going to talk about this before. Yes, if I can get multiple images, they're just simple Bayesians work. But then I've got to do the registration problem, which tended, and we talked about this earlier, there just isn't good registration stuff outside of Microsoft that was freely available. And so then I'm solving an entirely different problem. On an iPhone, on the original 4, I could trick it into taking 2 images at once, and then it stored the second image in swap space, and then you could just do simple things. You could do a Bayesian, or you could just do an average over the 2 images because they ended up being really registered. The camera would just flip twice, and it got rid of most of the noise. But I haven't been able to do that again. And the other problem is, even with this camera in a vise, so I clamped this into a vise on my desk, and I was playing with low light, and so I was taking a picture of the inside of my file cabinet with my camera in a vise. Just pushing this, even with the darn thing in a vise, moved me about 6 pixels on average. And so that was just another level of complexity. So I ended up, for mobiles, dropping down to a single image. But yeah, if I could get 3 would be magic, and all the noise goes away. So this is another low light and texture example. Let's see where I am. Wait, okay, I must have gotten rid of those slides. I had a whole bunch where I talked about noise. Oh, I moved them to the color section. Okay. So what I did was, everything I did was local adaptation. Asymmetric filter kernels. And what I started doing was orienting them based on flow images. So I can calculate optical flow really quickly, orient based on the optical flow so that everything runs, my filter kernels run in the direction of the optical flow. That worked really, really well. And then orient the filter. And that got me to here. So once again, it's pretty good, right? I'm still in this place where we're in the dark and the shadow. It's not really great. So I did something totally, I don't know, it's biologically inspired. In the filters, I started looking at the morph count, if I were going to use a morphological operator. So I look at the 16 neighborhood or the 8 neighborhood of a pixel, and I just invert the filter response. So does that make sense? What was happening right here, and this only works because I'm looking at a black and white image, right? But I look at the pixels, and I look at the 16 or the 8 neighborhood, right? Whatever my filter size is. And if I've got more black than white, I use the same filter response. If I've got more white than black, I flip it. And the only reason that I was able to do this is because there was an if. I get an if now in the shader generator. I get one if in my shader. So I can make this one if call. And then I just change that impulse response. That ended up actually working really well. Now, it's generated an artifact, but the artifact is pretty difficult to see. Because if you look at her hair right here, I've generated those weird artifacts where it's fence posting. I'm exactly right on those, where it's coming across and where it's oriented. And but it's okay because it just looks like a single fake hair, right? I'm in this very uniform textural visual field, and it's giving me this little artifact that goes across it. So then take this, do diffusion, do an anisotropic diffusion, same thing that we did back here, in black and white I just did it across the color channels, black and white. I'm anisotropic diffusion them, push it together, and that artifact goes away. And so that's what pencil effects is. And then if we just we can generate paper textures on the fly and blend her onto it, Once again, almost all of the noise that came out of the algorithm is gone now, right? And people just read it as the paper texture noise. But I really like if we look at her fingers and then her lips, it all looks pretty good. And then these are just some parameter variation changes. So I've got a couple sliders here where we can change the size of the filters. And then how much diffusion, and then the weight. How much weight we give to the diffusion image versus the edge image. And we get a variety of styles. But like I said, it worked fairly well. But it was...
Expose all these to the... Just basically a slider, some
Yeah.
sliders.
I give them a preset, and then there's a small, medium, large. That's the filter kernel size. And we have names for them, and I can't remember what they are. But you get a small, medium, large, extra large, and then sort of a blend one, and a...
I mean, essentially you let them play parameters,
Mhm.
saying, here's 10 combinations that we think you might like, pick one of the 10.
Right.
So that's the other,
And that's...
kind of the Instagram.
The Nokia guys push us for that.
Yeah.
And I didn't like it, because what we've found is if you give the user, if I do everything for you, you think the machine did it. If I give you some input, even if the machine did 90%, the user believes that they did it. This is the art that I created. Mm-hmm. And I did a graffiti app. I thought it was the coolest thing I'd ever done. But we did almost everything for you. All you did was type, and then you got these graffiti images. It was the coolest thing ever. In the backgrounds, I spent forever on this. I was able to embed QR barcodes, and they looked like the background. So to the human eye, it looked like a graffiti tag. But if you took a picture of it, you could read the QR barcode. So to be a tag, but the tag would take you to your website. You could use it for pricing, all kinds of stuff. People hate it. Hate it. Because the machine does everything. Mm-hmm. It's just typing. Who cares? And so, yeah, this outputs video. And I can output really great video, but this is what it looks like. This is a hand drawing a hand. It's that whole Escher thing.
If you really want to show us, you probably can go out of PowerPoint if the source file is there.
Let's try.
Of course, you have to figure out which cryptic name it is.
It's a problem with giving a graphics talk, right? It's either this one. This is the next one that I was going to show. So this is the magnification talk, the stuff that you were talking about before. The guys at MIT that have been doing the image magnification stuff so they can see your pulse. I'm doing something similar, but I'm doing it along the temporal dimension to give you a Cassidy Curtis style image abstraction. This is this one. But on the iPhone, this will run, I can do this on an iPad 3 in real time at about 30 frames a second. So I could pan it around, you guys could see it. But this works really quite well. I could show you this one. See, these things just pop and scintillate everywhere, but it's mostly along the edges. And see, there's some noise in the color space, but it's far higher when we get to that edgy kind of thing that we're doing, which makes a lot of sense, right? It's where the big changes are happening.
So among the effects that you've shown us so far, it seems like there's sort of the same low-level algorithm going on for every pixel or every area of the image. attention. You get, therefore, the same amount of detail everywhere, while some artists would abstract away the detail in places that are unimportant and just show you the detail on the faces or the things that they want you to look at. Have you looked at that sort of higher level abstraction and focusing the detail in places you want people to pay attention?
Yes and no. It's like I have two hats, right? So as an academic, yeah, I did that like with the cell phone stuff. When I take that hat off and put on the developer hat, no. There's a lot of apps out there that do that kind of thing. You know, you take a picture, I'll show you black and white, let you color on color, or let you scrub on a blur, you know, or paint on. So I'm going to blur everything except the part, that other part. So as a developer, I have to make money to keep my little shoestring startup going. And so I've kind of stuck with stuff that made money. And where there was a ton of competition and other people were doing it, I didn't, right? So it's, you know, a dozen of one, half a dozen of the other.
I'm not trying to debate this. I'm just thinking like one of the ways to eliminate the noise being distracting in the trees is by sort of just blurring that all away because it's trees and we don't care. Right? We care about the details on the people.
Right. And the real problem with that, at the end of the day, and I'll talk about more later, I need to be able to do foreground background. And I could do a simple one where I'd have you paint on the foreground, paint what's important, but that assumes that I have robust segmentation. And I didn't have really robust segmentation. And so later on, it's what I'm working on right now. It's what I'm doing today. Like my graduate student gave a talk on it last week. So that's exactly what I'm working on. I want fast, robust segmentation, and I want a very specific property out of that segmentation. So let's see, temporal abstraction, you guys saw that. Color algorithms. So here's where I'm just going to show you the slide. So there's the slide. Let's see if I can find me. Nope, that's the source. If you look at this, and it may be a little bit difficult to see because I've got this, I'm getting a ton of noise right there. And then if you look at my face, I hadn't shaved that day. And so when I move my face, I'm getting a lot of color noise. And then on the back of the chair where I'm sitting. And so this is one of the things I spent forever, like 6 months working on this. Like I said, the inversion stuff worked really well on the line images. And this is one of the things, it's not so much a technical thing, it's like, I went back to the drawing board, I said, okay, where does noise come from? Turns out that noise comes in, there's sort of two types of noise, random noise and pattern noise. When I started doing experiments, there wasn't a lot. Most cell phones aren't calibrated, but I'd have to get you to take your cell phone through this massive calibration step, like go into a really dark room, take 2 photos, and then I could get rid of a lot of the, like the dark current, the thermal noise. But getting somebody to do that for their phone most people probably wouldn't do it. And it was heinous. And then once again, I ended up with the segmentation thing. And here's, well, me wearing a hoplite helmet and showing you the kind of noise I could get. It also comes in sort of 3 flavors: signal dependent, temperature dependent, time dependent. And like I said, I worked on this for an entire summer, just looking at the kinds of things we could do, the kinds of algorithms that I could get. And in this photo, once again, if you could just turn down the light, I think the gentleman will do it. You can see a lot more of the noise. It's just because it's really light in there. But I've classified these based on the 2 different types. And this is, once again, me in a highly reflective hoplite helmet. And you can see all the different kind of noise that I'm generating that I want to get rid of. We can turn the lights back up, please. And what I found out when I started talking to users Doesn't matter. I'm like, what do you mean? It doesn't matter. And I'm like, huh? And I'd worked forever on motion and focus, right? How do I get rid of motion and focus? Doesn't matter. If the picture doesn't work, I'll take another one. It's my cell phone. I'm like, you're kidding. As a researcher, I'm like, no, this is a big problem. This is huge. No, we don't care. So that's my daughter, Zoe. Her dinner was too hot and she's fanning it, right? Well, Zoe, could you just hold the fan still instead of waving it? This is my cat, Percy, and he's doing both things. He's in the dark and he's moving as I took this picture of Percy being naughty. And it just doesn't matter. I'll take another picture. Once again, that was the thing. I went back to the books. I cooked up everything I could. I tried to do everything on the cell phone that I possibly could. At the end of the day, the answer to my research problem was don't care. That's what Percy was doing. Amazingly difficult. Students don't see the irony in this situation at all. This, however, I was able to get a lot of, I was able to do quite a bit of stuff. On a mobile device, two of the real problems that you have are low contrast, ultra low contrast. And then the stuff that I was doing was muddy. And like Jessica, this is one of my engineers, Jessica, if I can go into Photoshop and just pop her eyes out as white, she looks 10 times better, right? But the diffusion process, there isn't enough difference in the color near her eye and her eye color, and it just gets kind of muddy, right? But a comic artist would pop that out. You make this pop. You also do this weird thing where you make that, you know, that fold at the bottom of your eye about 10 times larger than it actually is. If you look at an artwork, artists draw those things so big that you could balance a marble on them. Because it's something that humans pay attention to. Once again, the psychology informs the art, looks at the computer science. And here, once again, this is how I work. There's a lot of evidence that Monet was actually quite nearsighted toward the end of his life. And you can see a lot of his artwork in the early phases is very, very tight. And then as Monet ages, everything becomes very, very loose, right? And by Garden of Giverny, it's completely just shadowy. What people believe now is that Monet painted what he saw. There's some evidence that Mondrian painted the apple tree in front of his house. This is Monet's apple tree evolving over Monet's life. Oh, sorry, Mondrian. That's his apple tree that evolved over his life. Turned out that he had a very large tumor in his visual center, near his visual center. So there's some evidence that the abstraction that he was looking at in the painting was based on this. Well, was Van Gogh colorblind? So there's a Japanese researcher, and I forgot to put his name on my slide, which is horrid of me. And here they don't look really different. And what this researcher had found was that he'd done a whole bunch of work with protonoic color blindness. And he built a fairly simple filter, and there's apps now that'll do it. Well, what would this look like if I were colorblind? Turns out if you look at Van Gogh's with protonoic color blindness, they look a whole lot better. So we took the Japanese researchers' work on color blindness, and the color blindness problem was an interpolation problem, right? I'm going in one, I know what A is, I know what B is, I draw an interpolation line. And the simple thing that I did is I said, okay, what happens if we extrapolate? Right? Because what in fact we're doing is reducing color contrast. What happens if we just use the same data, the color blindness, to increase color contrast? And once again, are these showing up really well on the, can you guys see a difference? Because on my monitor, it's fairly amazing. Okay, and so this is in the app. Okay, I think in the app we call this the Juiciness Filter. And this was inspired by Bill Buxton's intern who gave a talk at NPAR one time. He said, yeah, I want photos that look like this. And I don't know what word to use, but I'm going to call it juicy. I want juicier looking photos. So given all that, Katy Perry, where are you? I'm not seeing it though. Anyway, given all that, I can do pretty good video in real time on an iPad 3. And I just got a snippet of a Katy Perry video. You can see it. It looks amazing. The colors pulse slightly, but other than that, it's fantastic. Okay, and that leads me to where I am today, and this is what I'm looking at now. One of the problems that I have that a real comic doesn't is this thing that I call the coloring book property. So comic books were made on 4-color presses, and wherever 2 colors touched each other, the artist would draw a black line over that, right? And it's just an artistic convention. The reason was when the colors touched, everything got muddy. So you draw this black line over the top, and it's called a trap. So if we look at a coloring book, and I chose this one specifically because the artist who did this didn't do a perfect job, there's a couple places here that aren't trapped. And my algorithms give us that, right? I don't have a complete segmentation of the image. I don't have this trapping property. If I had this, if I could do this, suddenly the world's my oyster, for a lot of reasons. I can go have a conversation with Charles Loop, and we can take video. If I can process the video and get this property, suddenly I can go directly to implicits, right? So I can have an implicit image, but I could have an implicit video, right? And this is amazing because megabytes of video become kilobytes, right? Watermarking works. Almost every watermarking scheme you can come up with, I can destroy with a couple of affine image transforms. Grow it by an odd number of pixels, shrink it by an odd number of pixels. I can almost always erase your watermark. But if you could throw this process at the big image, at the small image, if it were close, bam, watermarked. This would work for search, right? I run this process on your image, save off this little implicit function as metadata, say, hey, go find me images like this, and then you just look at that image metadata, right? So that's why I'm doing this. The problem that I'm faced with is I need fast, amazingly robust segmentation. And that's what I've been looking at. This is what I did before. And the real problem with segmentation, I've got to enter in per image a whole bunch of parameters that show me how exactly do you do that. And so in the past, what I've done, and what most people do, is you over-segment. Make the things really, really tight, and then use some sort of watershed to simplify these regions back together to get coherent regions. And with this one, I also had I used face recognition, and I used Koch, Koch, Laurent, importance, saliency. So I would add the saliency information or the face recognition information to these before I ran the watershed, right? Takes a lot of time, not amazingly robust. And this is where the universe intervened and dropped a graduate student in my lab. His name is Ashlyn Richardson. Ash has been working on, Ash is 35, he's been working on segmentation his entire life. He was a quant in London, then he worked for the Canadian Space Association, and then he came and started working for me. This is 9-dimensional radar data, okay? And so what most people do, and what the gold standard seems to be, is k-means. So you do k-means simplification. So we're looking at satellite, this is, well, aerial data, an overfly with radar. And they've simplified this 9-dimensional, we use dimensionality reduction, ISOMAP and LLE, and we use a hybrid of those two to go from 9 dimensions to 5, which the radar community says are the most salient. So here's k-means clustering on those 5 dimensions, and here's our k-means clustering. right? We're far, far faster. And there's one, Ash showed me this. So these are trees. And so here's normal trees. These trees in this region are different than all the other trees because there was a forest fire here 25 years ago. And our data shows it, and the k-means doesn't, but the ground truth does. Ash told me this was really important. The one thing that we're doing, and now Ash calls these dendrograms, what he's really doing is looking at, it's multidimensional, but all we're doing is treeing, right? Same thing that you do. But when does your tree stop? And how do you look at your tree? And what everybody does is they say, okay, I'm going to do some sort of tolerance or distance parameter. And we did not that. We did algebra. So as you're filling up this tree type database, we look at secant lines based on what's the difference between adding this pixel versus not adding it. And we look for changes in the derivative, basically, right? So we're looking at secant lines. Is this thing tending toward infinity or not? And so we're finding what amounts to the first derivative of the change in adding a pixel versus not adding a pixel. But we're using an algebraic solution. We can't use a calculus-based solution. This, I think, and Michael said that there's a really strong theory group. Once again, I'm off the map of where I've ever been before. I've never seen anyone run an algorithm like this, right? Where I'm trying to run calculus based on how a data structure fills up, a calculus-based solution. But I know that I can find things that look exactly like minima, inflection points, and maxima. And it works amazingly well. It works so well that I can't show you how this algorithm works. Ash just got a letter from the Canadian military saying that they've given this the defense stamp. I can send you the slides because we've already given them. And I can tell you about, I can't tell you about how the dendrograms work. I can tell you about how our solution works to stopping, but that's our stopping criteria. But yeah, it works really, really well. And that's what I'm using. My hope is that if I can get a really robust segmentation, I've been using line interval convolution, but I've just switched to a third order Runge-Kutta to do smoothing. When the smoothing runs out, if I'm at a junction between two color areas, I'll just extend the line. And that's my hope. I'll do some flow-based algorithm that goes in between those regions that will give me this coloring book property. But it's one where I've got to back off now and see if I can prove that I have the coloring book property for every image that I run. Okay. Given that, a lot of what I'm looking at, I've used really simple rules for simplification, right? So I'm suddenly in a really target-rich environment. And these are rules that cartographers have for simplifying maps. And there's a ton of these, and these are other things that I'm looking at to help me with this process. How do I give myself this coloring book kind of thing? So these exaggeration, I'm going to find out what's important and exaggerate it. That's, if it's important, if I'm getting something on my importance function, I want to draw a line there. If not, I don't. There's things that I want to eliminate that aren't important, right? And how do I decide on what those things are? Right now, if it's something like this that doesn't enclose a region, we're calling it a texture kind of thing. Your eyes enclose a region, but your smile, the line of your smile doesn't. So I've got to leave that one, right? But maybe my eyelashes, where two things join, where a surrounding region joins a non-surrounding region, maybe those can go away. Typification. Can I just randomly get rid of some of the stuff in my image? And it turns out that under certain conditions, sure. If I throw a bunch of grapes at you, it's the same as throwing a tennis ball at you, right? Our visual system doesn't care. It's a green thing in motion. We really don't care. So if it's in motion, sure, right? Get rid of it. If it's still and it's important, then probably not. But if it's still an unimportant, like you said, throw it away, right? And then outline simplification. And once again, I think that once I can get an implicit, right, we can get an implicit following routine, then simplifying what an implicit function is becomes really, really easy, right? So I'm really not worried about that one. I think that's kind of automatic. The typification, I think, is going to be a rule set. Okay, and I just threw these in. I didn't know if I'd go overtime or undertime. This is just another thing that I built. All of our apps right now, you can create products. I've let that thing go. You can get it for free. It's in use in about 100 apps right now. So if you do something with graphics, create a product, I can beat the price of Cafe Press or Zazzle, higher quality, and the user gets 40%. Anyway, that's what I have. Thanks. Any questions?
Great.
Okay, toothbrushes and cell phones. I've heard this attributed to many people, but 6 billion people on the planet, 5 billion of them have cell phones, 4 billion of them own toothbrushes. I'm probably going to keep working on cell phones. All right, thanks for coming, folks.